Okay, let's talk about section 17.4 and equations of motion about a fixed axis. Fixed axis being the key word, so this is about a hinged point or a fixed point and something else is rotating about it. In this case, I've got this green blob and we're using, it could be an arm, lever arm or something too. But the point is we have some vector RG. Well, I didn't mark. Some vector r to g, or some distance, and that distance is fixed. Don't need the vector as much as the length. And let's turn that into a kinetic diagram. If this has a circular path, then that means we're going to have some normal component for the acceleration of g, and perpendicular to that, tangent to the path, is the acceleration of g in the tangential direction. Okay, that means we can apply the following. The summation of the forces in the normal direction is equal to the mass times the acceleration of g in the normal direction. What can we write the acceleration of g as, though? We've learned recently, if we know it's a fixed radius and we're given some omega, then we can just do omega squared r. And that's the distance r to g. Okay, we can also sum the forces in the tangential direction and get mass times the acceleration in the tangential direction for g. But let's rewrite that. The acceleration in the tangential direction we found is alpha crossed r, or alpha r, so let's write alpha times r of g. We now have one more equation. We can say if we sum the moments about g, it's this point, the center of mass of the body. We sum the moments about that point from all of these external forces that may be causing the motion, that it is going to cause the moment of inertia about g to have some angular acceleration. Alright, this is a new set of equations we can use. Previously we had said the summation of the moments was equal to 0. That was a special case where there was no rotation or angular acceleration. What if we wanted to do it about this point O? Often that happens to be a more clever point. A force may be going through it. So in this case, the acceleration or force caused by the acceleration in the normal direction would be concurrent with point O. So it could have its advantages. We could say about point O and sum the moments about there. Summation of the moment about O is equal to, we're going to use the kinetic moments about O. Okay, well, summation of the moments about O would be Rg times mass times acceleration, so the acceleration of g. And in this case, about O, we're only going to have that tangential direction component, the acceleration in the tangential direction. Then we have to add an Ig alpha term. Okay, now here's the trick. We can rewrite as the summation of the moments about O, rearrange these terms to be Ig plus mr squared all times alpha. Now this is the parallel axis theorem from, I think, section 1. It describes how you can find the moment of inertia from a different parallel axis of rotation by adding in this term and using the moment of inertia about its center of gravity. So let's take that, rearrange it, and call all of this stuff right here I naught. then this equation, summation of the moment, it's about O, becomes I naught alpha. Thank you so much.